All right, so this is the second section of Chapter 9. This is part 1 of 9.2. There'll actually be 2 videos on this. And we're developing the idea of the power series from what we had in 9.1. We're going to talk about this guy right here, or his addition, or his contribution to calculus. His name was Brooke Taylor, and he was an accomplished musician and painter. Now, he did research in a variety of areas, but is most famous for his development of ideas regarding infinite series, to the point that he actually has an infinite series named after him called the Taylor series. Now, suppose that we wanted to find a 4th degree polynomial of the form p of x equals a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x to the third plus a to the 4, or a sub 4x to the 4th. That approximates the behavior of f of x, which is natural log of x plus 1, at and around x equals 0. So what we're looking for is we're looking for a 4th degree polynomial that's going to behave like this function right here, this I'm trying to think what they call it, transcendental function. That's what natural log and e are. They're transcendental functions. And it's going to behave like this transcendental function around x equals 0. Well, if we make p of 0 equal to f of 0, then the first, the second, the third, and the 4th derivatives, and those are all the same, then we would have a pretty good approximation. So what we're going to do here is we're going to take our function, f of x equals the natural log of x plus 1, and we're going to evaluate that thing at 0. Remember, that's where we're focusing our polynomial approximation on, is 0, so that's where we're going to base it off of. So that's going to give us the natural log of 0 plus 1, or the natural log of 1, which gives us 0. Now, in our polynomial here, p of 0 would equal a sub 0. Because if we're doing p sub 0, that means this is 0, this is 0, this is 0, and this is 0, and all these terms cancel out, and we're only left with that constant. So if we want to approximate with our polynomial, well, when f is equal to 0, then a sub 0 must be equal to 0. All right, and then when we take the first derivative of that, we end up with f of x equals 1 over 1 plus x. And f prime at 0 is going to equal 1 over 1 plus 0, which gives me 1 over 1, which is 1. All right, now thinking about our polynomial here, p prime would be p prime of x equals a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus 4a sub 4x to the third. Now, all we're doing, guys, is I'm showing you what this thing right here should equal and how it corresponds into this part right here. You are not going to take the derivative over and over and over of this polynomial approximation. We're finding how we find them. So p prime of x equals this, and if we find p prime of 0, then x equals 0 means that term goes away, that term goes away, and that term goes away. So p prime of 0 would equal a sub 1. Well, if f prime of 0 and p prime of 0 is its approximation, then p prime of 0 should be equal to f prime of 0, which means that a sub 1 is going to equal 1. All right, and all we're going to do is we're going to continue doing the same thing around 0, and what's going to happen to all this stuff? Well, everything that has an x in it when we evaluate it at 0 goes away. So the next coefficient we're going to find is going to be the a sub 2. We're going to do it by taking the second derivative. So f double prime of x is going to equal negative 1 over 1 plus x quantity squared. All right, and when we evaluate that thing at 0, f double prime of 0 is going to give us negative 1 over 1 plus 0, which is 1, and that 1 squared gives us 1 on the bottom, so negative 1 over 1 gives me negative 1. All right, if we take the derivative of this thing right here to get p double prime of x, the a sub 1 is a constant. It's going to go away. We're going to end up with 2 a sub 2. The x goes away, and we've got this 2 is going to move to the front, and we're going to have 6a to the third x. And then this 3 is going to multiply times the 4, taking the derivative. Remember, a sub 4 is a constant. It's just tagging along. We have to multiply the power, so we get 12 a sub 4 x to the second. So p double prime of x gives me exactly what we're talking about right there. And then if we evaluate that at 0, p double prime of 0 equals just this part right here that has no x attached to it. So that one goes away and that one goes away. And p double prime of 0 is an approximation of f double prime of 0. And if they're approximating, we want them as close as we can, so negative 1 equals a sub 2. Negative 1 equals 2a sub 2, and when we solve for a sub 2 equals negative 1/2. All right, and picking up from there, if we do the third derivative of this thing, we're going to get 2 times 1 over 1 plus x quantity cubed. Evaluate the third derivative at 0, and we're going to find out that it's 2 times 1 over 1 plus 0, which is 1, and that 1 cubed gives us 1. 1 over 1 is 1, times 2 gives us 2. And then when we do the other side, we're going to take the derivative of this. So this constant is going to go away. Here we're going to end up with 6a to the third. And here, when we take its derivative, we're going to get 24a to the fourth x. Now, once again, p triple prime of 0 is going to be 6a cubed, because this x becoming a 0 takes this term out. And with our approximation, remember, these should be equal. So f triple prime of 0 should be equal to p triple prime of 0. So 2 equals 6a cubed, which when we solve that, we're going to end up with a to the sub 3 is 2/6 or 1/3. All right, and we wanted a fourth degree, so we're going to go ahead and go to take the fourth derivative. We take the derivative of this thing right here. We're going to multiply by the negative 3, and you're going to get this as the derivative. When you evaluate that at 0, you have f, the fourth derivative of f, evaluated at 0, being negative 6. Because 1 plus 0 is 1, 1 to the fourth power is 1, 1 over 1 is 1, times the negative 6 gives me negative 6. So then you're going to take the derivative of this thing right here, so that constant's going to go away, and this one's going to become a constant, and you end up with p to the fourth derivative of p of x is going to be just 24a to the fourth. And then when you evaluate that at 0, you're just going to get 24a to the fourth. These two things have to be equal, or should be equal if we're doing an approximation. If we're doing an accurate approximation, they should be equal. So we end up with a to the fourth equaling negative 6 over 24. Now, this will reduce, and I talked about this one reducing to 1/3, and this one's going to reduce to 1/4. But we want to leave it like this for just a second so you can see it. This is 2 factorial, this is 3 factorial, this is 4 factorial. You want to know those because that's going to be part of our equation we're going to come up with. We are going to come up with an equation for this. This is not the way you're going to do this. All right, so when we put all those pieces together, our polynomial approximation, plugging in a sub 0, a sub 1, a sub 2, a sub 3, and a sub 4, as we calculated them, we're going to get p of x is equal to 0 plus 1x minus 1/2 x squared plus 2/6 x to the third minus 6/24 x to the fourth. Now, like I said, these fractions, these last two at least, will reduce, but we leave them like this for a reason, so that we can see the pattern. And here's one pattern right here. So our 4th degree polynomial approximation of the natural log of x plus 1 is going to give us this thing right here, x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. Now, if we were to plot both these functions and look at their graphs, we're going to see that near 0, the functions match very well. Right here is my f of x that I've just calculated, or sorry, that's the actual function, and here is our polynomial. The red is the polynomial that we just found right there. So the blue is f of x, the red is the polynomial approximation, and notice right here around the blue, around the 0 value, those values stick together, those functions stick together very closely. And if we zoom in even more, here we can see just how accurate they are. They're around 0. Once again, the red is the p of x, our polynomial approximation, and the blue is our actual function. Remember, it's based right here. They are exactly the same at 0. And here we've got values around 0 where the approximation is very, very close to the same value. And not only the same value, but the same behavior. It's the curve is behaving the same. Now, notice that our polynomial that we've done our approximation for has the form of this. F of 0, that was our first term here. F prime of 0 times x, that's where we got our 1 from. F double prime of 0 divided by 2 times x squared. That's where we got this term, and the negative 1/2 was f prime of 0 divided by 2. F triple prime of 0 divided by 6 times x to the third. F to the fourth derivative of f evaluated at 0 over 24 times x to the fourth. That's where these numbers came from. That's exactly what we did. And here we have 0 factorial on the bottom, we have 1 factorial on the bottom, we have 2 factorial on the bottom, we have 3 factorial on the bottom, we have 4 factorial on the bottom, which just happens to coincide with what? The derivative that you're taking. Now, over here, you're probably thinking, well, 0 factorial. Well, if you remember factorials just a little bit, 0 factorial, there's no mathematical definition to it. It's defined 0 factorial is equal to 1. The reason why it's defined that way, and there's not really a mathematical way to do it, all the calculations we know how to do with factorials work when this is true, but there's not really a way to prove why it works. So that's where you get defined, something is defined as a value as opposed to where it's proven to be a value. All right, and here is the other way, which is the way we talked with the factorials on the bottom. Now, this pattern occurs no matter what the original function was. So if you've got any type of function that you want to approximate, you can approximate it with a polynomial using this pattern right here. And this pattern not only goes this far, but it continues on. If you wanted a 7th or an 8th degree polynomial, you just continue on and take the derivative over and over and over again. So this is the pattern. All right, and this pattern is called a Maclaurin series. A Maclaurin series is a polynomial approximation generated of a function at x equals 0. You will never have a Maclaurin series that's generated anywhere except for x equals 0. So if they say they want you to generate a Maclaurin series, they don't have to say x equals 0. You should know that. Maclaurin is always going to be generated at and around 0. It's based off of 0. So that's why we have f of 0, f prime of 0, x, f double prime of 0 over 2 factorial x squared. But that's the equation for it. So you're always going to have 0 here, 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 in all those places. Now, if we want to center our series and its graph and the approximation it's going to give us at some point other than 0, we're going to have to use a Taylor series. And the Taylor series that we're going to use is going to be this thing right here. Now, you're going to notice that this is significantly more difficult because you have f evaluated at a, which is not 0, f prime at a, but then you have to multiply by the binomial x minus a. Over here, you have x minus a quantity squared, x minus a quantity cubed. And if you want to simplify that down to a simple polynomial, then you actually have to FOIL that out and distribute and all that stuff. Now, we're not going to do much of that, but I just want you to know if you want to actually find the polynomial correct, the true polynomial, not just in this form, you have to cube this thing, multiply x minus a times x minus a, FOIL it out, and then multiply what you get there times x minus a again. Don't forget to FOIL. Don't think that x minus a quantity squared is just x squared minus a squared. It's not. Remember, you've got to FOIL it, and you're going to get, the actual polynomial there. So this is generated at x equals a, where a is some value other than 0, and that's a Taylor series. Taylor series is all-inclusive. It includes all this, but if we talk about the Maclaurin series, it's always based at x equals 0. All right, so let's do an example. We've got y equals cosine x. Let's go ahead and we're going to find the Maclaurin series for cosine of x. So f of 0 is going to be our first term, and it's 1. F prime of x is negative sine x. When we evaluate it at 0, we're going to get 0. F double prime of x equals negative cosine x, which is going to give us negative 1 when we evaluate it at 0. F triple prime of x is sine x. And then when you evaluate it, it's going to be 0 at 0. And then the fourth degree, our fourth derivative, is cosine x, back to where we started off here. And we're going to get f to the fourth. Our fourth derivative of f evaluated at 0 is equal to 1. And when we put all those values in, we're going to get 1 plus 0x minus 1 over 2 factorial times x squared plus 0x cubed over 3 factorial plus 1x to the 4th over 4 factorial. Notice we're only doing the even powers, where we're talking about x to the 0 being an even power. So here, this power goes away, this term goes away, that term goes away. We only have the even terms. P of x is equal to 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial minus x to the 10th over 10 factorial, continuing on and on and on and on and on. Now, here's the thing. The way I remember this is I remember that cosine is an even function. And guess what my polynomial powers are? They're all the even ones. That's just a little trick to try to remember. You can use it if you want to. You don't have to. All right, so what we have here, here's our cosine graph. And if we plot this polynomial right here on this same coordinate plane, what we're going to get, there is the first term and the first term only. So that would be a first degree, or sorry, a 0 degree approximation of cosine x. It's just a constant. Now the second degree, if we add the first and the second degree, or sorry, we add the 0 through the second degree, we're going to get a polynomial, in this case a parabola, that's going to open down just like that, based at 0, so it's really close there. And then when we add the next term, we're going to have one that's like this, and what do you notice? Well, it's a quartic, and what do we know about that? Well, notice that with the extra power, it extends out further where it's meeting that graph or really, really close to it. Right? When we go to x to the 6th, notice that this is a negative, so it's going to end up opening down. And that's really all we've got until it gets out here and does some crazy stuff. But there is your x to your 6th degree polynomial approximation. And notice that it's accurate almost out here to -2 and +2, even a little further past it. I mean, very accurate. So the more of these terms you use, the larger it's going to open up the interval where your polynomial is a decent approximation for it. So x to the 8th, since that's going to be a positive x to the 8th, it's going to open up. And there it is. Oh, nope, hold on. I went too far. There's the x to the 8th. And then the minus x to the 10th is going to go the other way, and there it is right there. And notice that it fits very well, almost all the way out to -4 and to +4. So the more terms you have for your Taylor or Maclaurin series, polynomial series, same thing, the more accurate it's going to be. Now, let's talk a little bit about the series and the polynomial. The polynomial is formed when you stop it here and say, okay, I'm not really going any further anymore, so let's get rid of those dots. That is a 10th degree Taylor polynomial. A Taylor series is when you leave the dots and imply that this thing continues on. Remember, a series that we're talking about is going on forever. So the more terms we add, the better our approximation, not only in here, but also out further from where we're centering our approximation. Now, let's look at the polynomial approximation for the Maclaurin series for y equals cosine 2x. Now, rather than start from scratch, we can use the function that we already know, and all we're doing is we're putting in 2x everywhere we had an x before, and then you're just going to simplify it. So you got 1 minus 2x squared over 2 factorial plus 2x to the 4th over 4 factorial minus 2x to the 6th over 6 factorial, etc., etc., etc. Well, what is 2x squared? Quantity squared. That's going to be 4x squared. So we end up with 4 over 2 factorial, which is going to simplify down to 2x squared. What happens when we raise the 2x to the 4th power? Well, we're going to end up with 16x to the 4th power, and the 16 over 4 factorial is going to simplify down, reduce, but you can do that all the way across. Now, most of the time you're going to be able to leave it just like this. They're not going to ask you to do any more. But if you needed to, this p of x is going to equal 1 minus 2 factorial, remember, is 2. 4 factorial is 24. 6 factorial is 24 times 5, which is 120. 120 times 6 gives you 720. And 8 factorial and 10 factorial you can grab a calculator for. But 2 factorial, or 4x squared over 2 would give you 2x squared. And then here we got 16 with the 2 to the 4th over 24. That's going to be, what, 2/3? X to the 4th minus, and then 2 to the 6th power. 2 to the 4th power was 16 times 2 is 32 times 2 is 64. So 64 over 720. And yeah, I'm not even going to try to reduce that in my head. But that would be how you would go ahead and simplify that down if you needed to. All right, so what about the cosine of x and approximating at x equals pi over 2? Well, we're still going to do the exact same thing, find all those derivatives that we need and their values at the different parts. So f of x equals cosine x, and cosine of pi over 2 gives you 0. F prime of x equals negative sine x, and negative sine x, or negative sine of pi over 2 is going to give you negative 1. F double prime of x is just the derivative of negative cosine x, or negative sine x, which gives you negative cosine x. Evaluate that at pi over 2. Well, cosine of pi over 2 is 0. Negative doesn't matter, so it's going to be equal to 0. And the third derivative is sine x, and the sine of pi over 2 is going to be 1. And the fourth derivative of our function with respect to x is cosine x, and that evaluated at pi over 2 is going to give you 0 again. So we're finding the approximation of the function we just found the approximation of, but notice we're moving it to pi over 2. It's no longer going to be centered at 0. So when we put everything in, we've got a sub 0 plus a sub 2, or a sub 1 times x minus pi over 2 to the first power plus 0 over 2 factorial times x minus pi over 2 squared plus 1 over 3 factorial x minus pi over 2 to the third power. And that continues and continues and continues. Now, everywhere we've got a 0, here and here over the 2 factorial, it's going to take those terms out. So our polynomial approximation is actually going to be negative x minus pi over 2 plus x minus pi over 2 quantity squared over 3 factorial minus x minus pi over 2 to the 5th power over 5 factorial, and that continues on. So this is a Taylor series, and if we cut it off there, it would be a Taylor polynomial, but the Taylor series, that is, or the Taylor polynomial, that is the approximation of y equals cosine x, but it's centered at x equals pi over 2. So when we're centering somewhere other than 0, notice it does look a little more complicated because it actually is, but we're still just plugging stuff in. All right, now here are some common Maclaurin series for the functions e to the x, sine x, cosine x, and 1 over 1 minus x. Familiarity with these common Maclaurin series will simplify many problems, so you should learn these and remember them. Now, this part right here, don't commit that to memory. I want you to learn the actual series itself. And most of these are very easy to remember. E to the x, notice we have all these terms. 1 plus 1 over 1x over 1 factorial plus x to the second over 2 factorial plus x to the third over 3 factorial. Then the next one will be plus x to the fourth over 24, or 4 factorial. So you're including every single one of those terms, and they're all positive for e to the x. That's just a way to remember it. All right, sine x, we talked about cosine x. We talked about what do we know about all the terms there. They're alternating. Notice that. They are alternating because trig goes through a cycle. But the big thing that I told you about was to remember that we're dealing with the even powers. And the way to remember that is that cosine is even. Well, guess what happens with the sine? The sine function is an odd function. And what are we using here? We're using only the odd powers. X to the first power, x to the third power, x to the fifth power, x to the seventh power. And we do what? We start off with positive, and the signs alternate the same way they did with the cosine. Just another way to remember it. Now, familiarity with these is good, but it's not as important as knowing what the actual series is. We'll talk more about this stuff here. And then f of x equals 1 or over 1 minus x. Well, notice here we've got all the terms we had up here, except we do what? We get rid of those denominators. So the denominators here go away. And the reason why that is because we actually end up with, let me get down there where you can actually see it here, 1 plus 1 factorial over 1 factorial plus 2 factorial over 2 factorial plus 3 factorial over 3 factorial. And those factorials are coming by taking consecutive derivatives. Remember, the x to the third, if you continue to take the derivative until it gets to be a constant, you're going to have 3x squared and then 6x and then 6, which is what? 3 factorial. So with the 1 over 1 minus x, the way I remember that is to just remember that it's going to be everything I've got with my e to the x, all the terms, but I get rid of the bottoms. So these should be committed to memory. Now, when we're referring to Taylor polynomials, we can talk about the number of terms, the order, or the degree. Now, remember, a Taylor polynomial includes the Maclaurin, so don't think we're excluding Maclaurin. Taylor is the one that gets it for every place, centered anywhere. Maclaurin is a specific type of Taylor polynomial that is centered at 0. So when we say Taylor polynomials, we're including the Maclaurin series as well, Maclaurin polynomials as well. All right, so this one is a 4th degree. It has 3 terms, and it's a 4th order. So when you're asked to do one of these, and you will be, they may ask you to write the first 5 terms of the Taylor polynomial for cosine x centered at 0. In that case, you would go 5 terms out. When you got to the 5th term, not including 0 terms, then you stop. Now, if they told you to take and write the fifth degree, they have done this in the past. If they tell you to write the fifth degree Taylor polynomial, this is what you would write right here. Because if you wrote the sixth one, you would be writing a sixth degree polynomial. This one, you're writing a fifth degree, except for what do we know about the fifth degree over here? It has a coefficient of 0. And the same thing with the order. The order and the degree are both based off of that power. And here's another situation there. The third order polynomial for cosine x is 1 minus x to the second over 2 factorial, but it is degree 2. If they tell you this, it's actually a degree 2 because it would only have to x squared. It wouldn't have a third degree. So if you were told to write the third degree, which they will write, they'll do that to throw you off a little bit. You don't go above that number. You may not write up to that number, but you're not going to go above it. All right, and a recent AP exam required the student to know the difference between the order and the degree. Remember, the degree, they're related, but the degree is actually the power itself. The order is based on the degree. All right, that's all of the first video for 9-2.